So guys, in the DNS masterclass, we will not only learn about the basics of DNS, like a website is linked to IP and all. We will also learn about how DNS work, why it has been introduced, and what is RFC 1034 and 35. And beyond that, like basically, you can basically actually understand the DNS existence of it, how to debug DNS in production and all. So let's start. So who's this who is this video for? Basically, if you are a front-end engineer, back-end DevOps or security engineer, you have to learn about the advance of DNS, like why it is exist in the internet system. And for if any of this profession is belong to you, then you can definitely watch this video. And what we are covering in this like today's topic, what is RFC 1035? RFC means request for comment. This is a system that is introduced in 1970, in which basically we will learn more thing about it. Let's see. And also resolution flow, recursive and iterative, how DNS basically find which website I have to serve to the user, what are different type of records like ANAME, CNAME, MX, what they actually mean is, and why they have exist. TTL and the propagation myth. So different type of propagation that DNS use. For example, why whenever you change something in DNS or update your DNS, then you will not see immediate effect of that change. That is because of propagation. We will learn about all of this. Bugging with the real failure. Like you can actually learn the command to debug a real failure, whether it is a code level failure or a DNS level failure. Different we also see a system design of network case study possible in the given timeline of this video. So this is all the things that we have learned in this video. Let's start. So this is the zero to hero class. You can understand all of these things that is written here. And let's see from the very beginning in 1970. So when there is no DNS, so basically this is the host.txt era. So everyone is relying on this file. This is basically the DNS in early age. So basically, the ARPA net era, every computer maintained a local text file called host.txt. It was a simple list mapping IP address to a hostname. So imagine you are in 1970 and you have a computer and you want to see Amazon.com, although Amazon.com doesn't exist at the time. For example, you want to visit to a abc.com page, but this is not possible because DNS is not there. So everyone has to maintain this host.txt file. So your in your PC or your laptop, your system, you have to have this file. In this file you will mapping abc.com means go to 1.2.3.4 IP. Similarly, a like you can say one amazon.com example. I'm just taking a rough example. You have to go 2.3.5.4. So this is the system that is basically the DNS at the time. So every PC has to this, and this is not scalable because if the internet grow, more people know about the computer, more people buying computer, and this has become a bottleneck because everyone has to maintain this file, and this is has a no fault tolerance. Because if anyone, because how it works basically, there is a in Stanford Research Institute there is a master file. So everyone has to update download that master file into their system. So whenever new person come, he basically inform the Stanford Research Institute that hey, listen, I'm Dheeraj, I bought this PC, and my IP is this. So Stanford Research will update their host.txt, and then everyone else will download this host.txt into their PC so that they can connect with each other, right? Host.txt. And this is not scalable because if anything happened here, it will impact the entire ecosystem, because everyone, if someone has mistakenly replaced abc.com to this and this to this, and the related all the ecosystem who is accessing abc.com will be get a failure, or they will be not getting the actual data of abc.com. So this is has no fault tolerance. So in 1983, person named Paul Macopatrich, sorry for the wrong pronunciation if I had, proposed a distributed solution that would become a DNS we use today. So he introduced a system, like he said, hey, look, this is a very wrong approach that we are following. Let's follow this approach. This approach is what, like, instead of centralizing a host.txt file and giving to responsibility to this Stanford Research Institute, let's have a distributed system that will automatically update every time a new PC come, right? And he also say that this is not, the existing system is not scalable because you can add hundreds of PC IP, but you cannot add billions of record, right? And in the end, you have to say it, like if a new person is coming to your ecosystem, this is very slow approach. He has to have to send the details that person to Stanford Research Institute, and there is one person sitting there and he is updating that host.txt file, and everyone else is downloading again that file again and again. And but in this new approach, it is a very instant, like nearly a second will take to add new person to the ecosystem. And which invent a DNS hierarchy. It is an inverted tree. Inverted tree means which is going downward. So it has three layers. First layer is root server, second layer is TLD server, and third layer is authoritative server. So we will learn about all of this. So root server is a dot server. So everything start with a dot. And for example, if you are visiting like for example amazon.com, amazon.com, so here is a dot, it is your root server, and then this root server will check the TLD, but whichever comes after that, which is .com. So .com become your TLD. Like here you can see .com, .net, .edu, .org. This is your top level domain, and .in is also top level domain. You can say now AI era, so .ai is also top level domain. And from this it can find who, like .com, in this .com I have to find the Amazon, which is the authoritative server. So who hold this authoritative server? Like you cannot connect your domain to multiple authoritative server. For example, route 53 is one, Cloudflare this one, Versal is one, and then Netlify is one, and DigitalOcean and so on. So this is your authoritative server. So if you are attach your Amazon domain to route 53, then you cannot attach the same domain to Cloudflare. So that you can also try it, it is not possible. You can only update to the one authoritative server, and Amazon, it will find that Amazon belong to .com. So .com has a one authoritative server, which is route 53, and route 53 is saying that I hold Amazon.com. I have all the like information about this domain, which page to serve, like who own this and everything. If similarly byte go is deployed to Cloudflare, then Cloudflare will tell, one second. So Cloudflare will tell like I have on this domain, I can serve this domain to the user. So this is how all the logic work from root server. It finding the TLD top level domain, then to TLD find the authoritative server who own this domain. Like for example, it is a route 53 Cloudflare. So in future, if you want to like build your own authoritative server, then you have to follow this hierarchy. So this is the very important part, the resolution journey, recursive versus iterative. So now iterative is almost like nobody is using it, but yeah, you have to learn about like how it's working internally. The recursive query is basically find your browser is telling the resolver. Resolver is basically the person who is responsible to find this domain for you and serve to your browser. For example, your provider, whether you are using a broadband or you are using a mobile internet. For example, you are using a mobile internet named Airtel. So Airtel is your resolver, and it's their responsibility to find this website and serve it to the your into your browser, because you're using their internet, right? And in the recursive query, your browser will say the resolver to find that google.com and serve to me, and that resolver will ask to the each for example each this server one by one, from root to TLD and then to authoritative server, for example Cloudflare and all, and then serve to you. This is the easiest, I guess, the easiest approach, like fastest approach for a resolver. And this is the iterative approach. Your resolver will ask, for example, Airtel will ask the next root server, and root server will say like, I don't know the answer, ask this .com, and then .com say I don't know the answer, but I have the information of the authoritative, for example, Cloudflare and so on. Let's understand it better. For example, here in Visual A, this is the iterative query and this is the recursive. In iterative, for example, this is your PC, you are just visiting google.com, and your google.com will request will go to your local DNS server. Your local DNS means so the local DNS was not here, because it lies somewhere between here, local DNS. Depending on, this is basically which provider internet you are using. For example, you are using Airtel, Vodafone, Jio, or any other company in internet, so they will work, they will serve as a local DNS server. So your request will go to your local DNS server, and it will go to root DNS, which for example dot is the root DNS here. And dot will saying like, hey, you are visiting amazon.com or google.com, so I don't have the information. You can ask .com as a TLD for this information, and it is sending a request packet back to your local DNS, and local DNS will then ask to the TLD, hey TLD, can you give me the .com google.com web page? And TLD will say, yeah, I know, I understand that this domain is ending with .com, so I am the responsible person, but I don't have the information about this web page. But you can ask the authoritative. I have the information of authoritative who own this Amazon or google.com web page. So he say, okay, so tell me the authoritative information. So yeah, so he's sending the authoritative information to your local DNS, and then your local DNS will send this request to the authoritative, for example AWS or GCP, or wherever the web page displayed, Netlify, Cloudflare. And he will say, like the authority will say, we have this amazon.com deployed on our infrastructure, and this is the IP of that, and this is the web page you can access with that, and it is sending your local to your local DNS, and then your local DNS send it to your computer, and your computer will show that website to your browser. So this is, you can say, this is very iterative approach, like request going this way, again then going this way and this way and this way. So every time a new server involved, it is sending a package, or package means the information to your local DNS, and then the local DNS again sending that request to different server, and then again this loop goes around. But the fastest approach is recursive approach. So in this is your PC, and you're sending request to a local DNS to find for example, Instagram.com, and then for example Google.com, Instagram.com, and then it is sending that request to DNS root level. Okay, so it is .com, so I will send to root level, and then this root level DNS server will not send this to back to your local DNS. Like it will not say like I don't know, but ask like initially in iterative, I don't know, but ask the next server. This is the approach. But in the recursive, it is basically sending one time to resolver, and it is the whole responsibility of the next server to find who owns this website. So here DNS will check .com, and it will send the whole website to .com, and .com's TLD domain, top level domain, will find the authoritative where this website deployed, and this is for example GCP or AWS, and AWS will send this website information back to the requester. So in this way, like request comes from this way, this way, this way, this way, and this way, and then goes back around this. So as compared to this approach, like this approach, this one is much faster, and it is has been used by most of the local DNS resolver. And also like local DNS resolver means your internet provider. So have you heard about like whenever a country or a state has imposed a ban on particular website, so they cannot like enforce that rule to the root server, because they are not the owner of that root server. They can simply telling your local DNS provider, hey, someone, if someone is visiting to this website ABC, then do not send the request to further root level server. Just stop there and send a response back to the user. So that's how they work like this, because they root local DNS server have authority, because you cannot access the internet directly without local DNS, like for example your broadband or SIM provider, right? So that's how the things work. So I'm just telling you this example to understand it much better. Okay, so this is the packet path. Browser go to resolver. Resolver is basically your local DNS provider, and then there's one DNS and local DNS. Both are different things. The resolver is basically your internet provider, and they send a request to root domain. Root sent to TLD. TLD sent to authoritative, where is website deployed, and then authoritative serve the final website and return back to the browser. So that's how it's works. So there is a different type of DNS record. This is the example. Like you can see AAAA, CNAME, MX, NS, PTR, SOA, SRV, and TXT. So this is the different name. There is more than this, but you have to understand these are the most common one that you have to understand, and also the name server. So for example, let's start with this A record, AA, and CNAME. So A record, like 99% whenever you send a request to like 9 or 90, but 100% whenever you send a go to web page, then every time that your root server will have to return this this record, this DNS record from the authority. The authority will return this DNS record. Basically it is holding an IPv4 address, the most common record type used in the point domain to server. For example, if google.com, it is pointing to 1.2.3.4, which is nothing but a address of a machine, and it is basically this record is saved in as a record, right? And this is the AA, means the modern architecture. Like previously most of the things, like most of the people are using IPv4 address, and now it is recommended to use AA record and store IPv6 address, essential for scale and mobile network. But yeah, right now still people are using this, but yeah, recommended is this. Now people are slowly shifting toward the AA record. And this is the CNAME record, which is similar to a record, but it has a one twist. Like for example, if your website name is www.debugwithdheeraj.com, which is my website, and for example, let's take example of amazon.com, right? Amazon.com, right? And if you add in starting of it like india.amazon.com, then this record uh, fall under a CNAME record, because this is a subdomain of your main website. This is your main website, and this is your subdomain. So this record comes under a CNAME. Okay, so CNAME, A name, CNAME, alias, MX is basically for mail, and AA. This is the major DNS name type that you have to understand. So this is the another way. Like MX exchange is basically used to redirect traffic to a particular email. For example, if you have a like a professional email, for example, support@amazon.com. So that is like when you send a email to support@amazon.com. So how your root server will like how your mailing system will find that which who hold this basically email, right? They used to find this with MX mail exchange DNS server. So in this DNS MX, it is a mail exchange record that will send your mail to this particular owner of this email, right? And TXT record is to use to verify the DKIM and DMARC property, that is also a part of emailing system. And this is name server record, and this is SOI record. You can learn about this if you want. But yeah, AAAA, CNAME, and MX. This is the four main thing that you have to understand. This can be asked in the interview as well. TTL, the propagation myth. So this is the very important thing. But before this, I wanted to understand, like we previously learned about this, right? Like how this resolver work, like how your local internet provider find the particular website to you, right? And this is not the every case. Every time you visit google.com or every time you visit amazon.com, your local resolver will not do the same step again and again. They will basically store, like find the IP one time and from here, and then store it to their memory, so that next time you're sending a request, they don't have to go to this path again and again. So this is basically caching layer, right? So this is the caching mechanism. So this is happened at your browser level, your operating system level, resolver means your internet provider level, and your CDN or app level, your load balancer and everything. So your browser do the same thing. They store the IP of that particular google.com or amazon.com you frequently visit on the browser. Operating system also do the same. They also store some data, like which website you visit frequently. So they store their IP address, and resolver is also doing the same thing, and CDN is also doing the same thing. So most people think about like DNS. Basically, when you upload a website, for example, you upload a google.com and add their DNS as 1 to like a record, basically that we've learned previously, a record as 123.4, and you visit to google.com and you see like it is working fine. Your web browser is fetching this data, and that means your a record is working fine. And you for some reason you updated your a record to 3.4.5.6 or something like this, right? And you again visit google.com, but this time this will not work. But eventually you see that this data is right. Previously it was this, but for some reason you change your authoritative or you change your server IP, and this is your new IP, and it is working fine on some computer, or might be not working fine on your computer. So this is the reason most people think that it will take time to 24 to 48 hours, right? But that is not the case. It depends on the what TTL you have set, because every time you update something, na, you are setting its TTL. After a record, you are setting IP, like a value of that a record, and you're also setting a TTL, time to live. Time to live basically at what time after like this data will stay there. Like you think that you updated from 1 to 3.4 to 3.4.5.6. You say you feel like you have updated, but eventually in the background it is still there for this data is still there for the TTL value. For example, TTL value is like 5 minutes. So 5 minutes there, in this 5 minute duration, this data will still serve to the user, right? This will not get effective. This will get only effect after 6 minutes, right? So DNS changes are instant. You are updating these changes. This is instant. Old cache simply take time to expire based on the TTL. So this is based on the TTL, but TTL is set. So recommended is 300 second, which is 5 minutes. But yeah, not more than that, depending on the requirement. So this TTL will use by browser, by operating system, the resolver and CDN. They all will store this data for 5 minutes, no matter you have updated it or on your authoritative level or DNS level, who is your authoritative, like Cloudflare or AWS or Netlify or Vercel. No matter what you use, this will the value you have set in TTL. All so that for that time your this level of browser OS will use the same value, and after that time is passed, they will again send a fresh request like this to this like this, and they will send a fresh request and file the updated IP, and then again get back and save here, and then send to you. So this is how it will work, like propagation. This is called a propagation myth that you have to understand, right? So now come the interesting part, debugging like a pro. So whenever your system fail as a software engineer or as a front end, back end, or DevOps engineer, your first responsibility is to check whether it is a DNS level failure or a code level failure, right? So to find that, you have to understand some basic command like dig example.com or google.com, git trace example.com, and so on. So this is some basic command depending on what platform you are using, Linux or Windows. In Windows, we have a ns lookup command, lookup. So we will not use any GUI tools for that. There is lots of GUI tool, but we will simply check how to check if that particular if the web page is not accessible. This is a DNS level failure because you have recently updated, or your team might have recently updated a record or CNAME record, or any record that is related to your domain address. For example, if for CNAME this is a subdomain, and for a record there is a main domain, and we have to read the output of that particular command and see if that record has been updated to a root server or not. For example, let me show you like how you can check. For example, I'm on window, so I will use ns lookup command, ns lookup, and here you have to simply add your website name. For example, google.com. So it is basically send it a fresh DNS request, like it has bypass all the caching layer, for example, operating system cache layer, browser cache layer, or your like a resolver cache layer, for example, your internet provider cache layer, and it has given you fresh DNS record, and it is sending like this address like has been timeout for this. Okay, so this is the address, and this is the IP, different IP of this google.com. Let's check my own website, which is debug with dheeraj.com. This website is live and deployed on Cloudflare, and then see and we will also see the Cloudflare DNS record if this is matching with the record that is in our Cloudflare server. So it is taking a bit time. So yeah, it has fetched this record freshly, and it is given us this IP. This is IPv6 and this is IPv4. So basically the point here is like you can use this tool if there is any change in DNS server and your website is not accessible. You can just run this command, and then you can find the which address is there and what address you have updated in your authoritative server, for example, Cloudflare or Virtual or wherever your website is deployed, and then you can trace the issue from there. And the real world failure is, for example, uh, NS domain error code, server failure, no error is domain exists but specific record is does not exist, missing glue record, common outage pattern, CNAME chain explosion, one NS server down. So there is if there is multiple NS server, then there might be one NS server down. So this is something that you can explore. But yeah, this is the real world error code, the most common error code that happened in DNS failure. So DNS in system design, the Netflix example. So Netflix using a very non-traditional way of using DNS, because the traditional way is DNS is routing to a authoritative server. For example, if you are visiting netflix.com, so ideally it should ask the root server and root server to TLD and TLD to authoritative server. But like Netflix doing is Netflix basically uh, it using a smarter way named GeoDNS, the ISP aware of routing, to send user to the closest Open Connect server. So Open Connect is Netflix own CDN, content delivery network. So they are basically finding, like if you're visiting netflix.com from India, then they will find the nearest Open Connect server on India, and then they will connect or serve data to you. And if you are visiting Netflix to from the USA, then they will find the nearest Open Connect server in the USA, and then similar to that. And they are also checking your ISP, like if you're using Airtel internet or Idea internet, or for example, not Idea is not no longer here. So they're basically using Airtel internet or Geo. Based on that, they are simply routing to the your nearest Open Connect server. So they have a multiple Open Connect server, CDN server basically, to minimize the latency and bandwidth cost. So DNS happened before TCP or TLS handshake. So if you don't know about TCP and TLS, this is basically a protocol. So TCP, like let me give you a basic understanding of it. Like TCP is basically you call a person and you say hello, and the person reply hello, who are you? And then then you acknowledge, yeah, that that person has listened to your audio, right? So TCP is basically the same thing. Like it is asking a server, can we connect? And like I want to connect, and server say like, okay, I'm ready to connect. Then it is saying like, okay, let's connect with each other. And TLS is basically like after this connection happened with your server, TLS say let's make it secure, let's add a encryption layer. So Netflix work in the same way. So before it's making a TCP connection or TLS handshake connection, it's finding the nearest Open Connect server to your location. Like if you're in Gurgaon, then there might be possibility there could be a server in nearest to your location in Gurgaon, and then it send a TCP handshake request. Let's connect this user to this server, and after this connection happen, it's saying that let's make it TLS more secure server, and then adding an extra encryption layer, and then it's sending you the movies or series that you want to watch this way. And how it's working, like for example, it's basically using multiple A reports. For example, if Indian user, there is for some reason India server has go down, but Netflix can't afford this. They have a huge market in India, so they immediately switch to a different server which is in US. Although it will increase some latency, but they will automatically, the Indian user will automatically get data from US server of Netflix. So basically, they have to update their A record in their authoritative, and make it 60-second low TTL, and this can massively shift amount the traffic globally without reaching application code. So they don't have to change the code level changes for this kind of thing. They just have to update the DNS record, and it will happen automatically. So first thing, like they're basically using their own way of caching, which is Open Connect here. They're using Open Connect. And DNS versus load balancer. While load balancer handle regional traffic, DNS is a backbone of global server loading balancing. So they're using DNS level caching. Basically, this is called a DNS level caching. So they are not using traditional way of routing traffic. They're caching on the DNS level, which user it is, where he is located, what internet provider he is using, which country he is living, and based on that he is just sending it to the nearest CDN server, which is the name they name as Open Connect. It is extremely low cost and infinite scale, and it has a zero latency, like not zero latency, but yeah, compared to another routing method, it has a very less latency and is stateless. And also, as compared to normal load balancer, it is a high regional limited added hoc. You can have to traverse, you have to ask the root server and then TLD and then so on, and it is a stateful. So this is the Netflix example how they are using DNS caching. And this is the hands-on DNS code that you can try on Python and Node.js. They have their own module, DNS.resolver and required DNS.promise. In this, you can write a normal code to check, to look which IP address of this domain belong to, which record. If you want to find a record, you can specify the a record and MX record and so on. So in this way, you can just simply see how DNS work in a code level. So yeah, the summary for this video is like DNS work in hierarchy. It from the root level to TLD to authoritative server, right? Caching is a king. You have to control the TTL, and based on the TTL, your new changes will be propagated to user browser based on this, right? And protocol over UI. So RFC 1035 is basically a rule. So RFC 1035. So every time anyone want to make a change in DNS, so they have to like add a request in RFC, request for commit. It's like a GitHub. When you add some commit in GitHub repo, then you are basically adding a comment like I have made this change. So similarly, for DNS, RFC is a GitHub, work as a GitHub, and everyone add a code, and everyone add their comment and to make these changes. So DNS come there in 1035, commit number 1035 and 1034. So here all the information about like this. So if you search on Google like RFC 1034 and 35 code, so it will give you the PDF of it, like PDF to read. In this like users explain like how DNS work, how should we use, and till the current time whole world is following these two PDFs, these two comments, right? So lower the TTL before any migration. If you want to do migration, lower down your TTL, see if it's not 15 minutes or 1 hour, make it to 300 seconds, so that within 5 minutes your changes will revert to the user. So anything happen bad in the production, try to dig first the DNS before moving to the code. Never mix CNAME with other record, and CNAME is basically subdomain. For subdomain, you add the CNAME as we understand earlier, and monitor SOA serial for zone sync issue. So if there any issue, and you can just check your SOA serials and see if this DNS level, what part of DNS level issue is this. So this is the whole summary. I hope this you like this video, and I will attach this PDF link in the description so you can go through with it. Okay, guys, thank you for watching. Bye.